All right, let's establish at least the things that are common among us for this. Lots of people may have come up with some different equations for this. In fact, a second ago I asked you please come up with a second one or a third one if you can. Let's try and express this in as many ways as possible, just for fun. But one thing we all can agree on, Gabe, is the amplitude, right? What's the amplitude? And Bryn, what's the what else can we agree on? No matter what our equations are.
Probably that the period is 2 pi over 3.
And how'd you figure that out?
Well, from one bottom point to the next bottom point, if there's a period of the cosine graph, it's 2 pi over 3 units.
All right, there you go. She looked at it. One way to do it. Now, to be fair, what if I hadn't had these markings in between? That made it kind of easier. Like, oh, this is 1/3 of pi, so that's 2/3 of pi. But if I didn't have those demarcations in between, I just had pi there. There is another nice way to figure out what the period is. This is a distance of 0 to 2 pi, right? And how many cycles are there? Right. Oh. So 2 pi over 3, right? Would that make sense too? It's kind of if you're like. So if you're ever like, and we have this worksheet that has a whole bunch of these on it for you later this week. Yeah, tomorrow, something. Yeah, I think we give it to you tomorrow. And that might be a nice trick that you'll use. So you didn't necessarily have to use that here. But I think we should all agree that the period is for all of us is 2 pi over 3, meaning that b is what? Yeah. Room. What else can you agree on? Anything else that we all definitely have? Say it again, sorry. I'm not sure we all do agree on that, actually. But you said h is 0? Okay. What's the other thing we're missing? K. I think we should all agree on K. What's that? 4. And A is, well, I don't know, plus or minus 3. So we have A, B, K, and then H is up for grabs as well, right? Like that might be depending on what equation you have. And now I'm ready to hear finally what equation you wrote down, Claire. How about you give one? Does that work? Somebody say yes? Yes. Okay. Give me another one that you found works. Piper. Did I write that right? Is that what you said? Is that what you said? Okay. Do you agree that that works?
Yes.
What else you got? Is that you raising a hand, Shivani? Go ahead, give us another one.
3 cosine 3 parentheses x minus pi plus 4.
Sure. Give me another one. Someone else. One more. By the way, there are an infinite number of correct answers here. So if you're not giving me another one, it's just because you're lazy, not because they don't exist. There are an infinite number of other answers. Give me another one, Chris.
3 cosine of 3 times x minus pi.
Whoa, slow down. 3 cosine of 3 times x minus pi. Check that one out. Does that look nice on there? Okay then. Okay. Yeah. Yeah. How would you generate more examples? Just in general. Yeah, so like we could add in here any multiple of 2 pi over 3, right? Add that to this number or subtract it, and you'll get another good model for this. Good. The homework was feeling good. Are you feeling good about A, B, H, and K all thrown into the mix? You like that? Sad that they didn't make you graph, really. You weren't sad about that?
I was
Broken-hearted is how I would describe it. anyways?
No, I was very skeptical.
You're skeptical. Would you like to talk about modeling problems today a little bit? I know you would. Give me some examples that you remember from last year, because this will be, to some extent, a matter of review again, too, of things that can be modeled by sinusoids nicely. Ferris wheels.
Waves.
Waves. What else?
I just repeat that.
What else? Ferris wheel and waves is all I've heard. Bicycles? What do you mean by bicycles? The wheels on the bicycles? What do you mean by wheels?
Hell no. Let's go.
Come on.
All right, so thank you, ladies and gentlemen. So the waves or tides, someone said up here. Looks like you have a problem like that we'll look at today. This is not an exhaustive list of examples that we'll be looking at. Average monthly temperature, it looks like, is an example, apparently, of something sinusoidal, approximately. A pendulum swinging, I guess that's maybe got some sinusoidal action going on, okay? What else isn't on this list? Ferris wheels you mentioned. What else did someone say? Any other things that are sinusoidal? List them. Springs? Yeah. In a mattress? Okay, how they bounce up and down if you let them bounce. Yeah, if you attach a little mass to an end of a spring or a slinky and let it go, it should be, something called simple harmonic motion. It should generate a nice sinusoidal height against time graph. What again? What else? Certainly other things that move in circles, right? Like the height of your foot above the ground as you bike. It's provided that you bike in a generating uniform circular motion. What else? Predator-prey models are sometimes sinusoidal as well. Predators, like if you look at the population of rabbits or something, you get something sinusoidal maybe. And if you look at the population of foxes, those might go 90 degrees out of phase with that. When just as the fox population is increasing, the rabbit population starts to go down. And as soon as the rabbit population goes really far down and hits a minimum, the foxes start dying. So those go down, right? So you have two sinusoids living happening.
Bless you.
Yeah, we should do a demonstration of the unicycle too. That's right.
Good for you.
Anything else that comes to mind? I guess one thing before we even launch into this first example, that I have kind of a deep question for you. I think this is kind of the quintessential first example that you probably used last year was the Ferris wheel problem. And I'll tell you why that's an important example, and then I'll follow that by giving you a pretty deep question. Okay, so be prepared. The way the Ferris wheel problem was like this. I'll just remind you. You were like, I don't know, here, this is like, say this is a 20-foot radius Ferris wheel, and the middle is 25 feet off the ground, kind of typical problem here, right? And say that we're like at, I don't know, 35 degrees here. The question is, like, what is an equation for your height at this particular moment? What is your current height off the ground? Well, this part is 25, yeah? Do you remember thinking through this? Yeah? Well, the only part we're missing is this piece. So what is that piece? This is the radius of the circle, or the Ferris wheel, is 20 feet, and this is 35 degrees. So what would that be? How would you compute it, at least? If this is 20 feet, and this is 35 degrees, what's the height of that triangle? That's a right angle there. 20 sine 35, right? Right? Or in general, that's how you compute the length of that red segment. If this is 20 feet and this is sine 35, the height will be 20 sine 35, right? You done that before? Thought about it? You can work it out again. Okay, all right. So I think you've thought this through before. And in general, if we don't know what angle that is, then we actually have like a function, don't we? Right? For any angle, I can now tell you what the height is. Yeah? And that works why? Well, because if we're over here in this second quadrant, so to speak, does that still give us the height? Well, sine will be positive there. I think it'll work. And if we drop below the midline, well, shouldn't we be subtracting something? Why does that work out, though, even if theta is like 200 degrees or something? What's the deal? Well, this will still be 25. What if theta is 200 degrees? Will that work still? Will that model this everywhere? Why does it still work if theta is 200 degrees? Do you hear what I'm saying? If theta is 200 degrees, we're actually here, you know? So doesn't that mean we need to do 25 minus that distance?
Yes.
So does the model work? Or why does it still work? It seems like we should change this to be 25 minus when theta is 200 degrees. It seems like we need to change the formula. Go ahead, Chris.
Here's the thing, even though it's 200 degrees, so sine can be negative.
Oh, so that takes care of it. The way we define the sine function is actually super useful to us. Oh, okay, that's right. Yeah, so it makes sense why maybe sine being negative at a particular moment makes sense to us. Anyway, the point is, this is very clear to me. And by the way, theta, we could maybe make theta a function of time too. Maybe this will be, instead of a function of an angle, I think a lot of times you would want to know where we are at a certain time instead, right? So your equation might look something like that, or something, I don't know, depending on how fast the Ferris wheel's going. And then you might write as a function of time instead. Anyway, you've had this conversation before. It's very clear to me in the case where we have something rotating. I think in the homework tonight you have there might be a carousel problem, but there might be a record player, I think, or something like that, and you're tracking a point and distance away from the wall or something. Whatever. The point is when you have uniform circular motion, the pedal around the bicycle wheel or something above the ground, makes very clear sense to me why we get a sinusoidal model, right? We just did the modeling problem right there, right then. But in other cases, like the tidal problem, where's the circle that's going around? I mean, that's not as clear to me why we get a sinusoidal model. It's clear maybe why we get something periodic, but why would it necessarily be sinusoidal? That's something for you to think about. I don't know. Why is it true that we get these things even when we don't seem to see a circle anywhere? Or even something as simple as a spring going up with a mass on it, going up and down. We get perfect sinusoidal behavior. Not an approximation. It's perfect. Why, though? I don't see a circle. Right? Anyway, just something for you to think about. That's the deep question. Okay, well, now let's go back to doing these problems here, which I think are of a type that you maybe have thought about before. I don't know. Kira, would you read the first example for us here?
On January 1st, 2008, the first high tide in Ocean City, Maryland occurred at 2:11 a.m. At that time, the depth of the water was 1.9 meters. The first low tide occurred at 8:14 a.m. at a depth of 0.4 meters. What was the approximate depth of the water at 6 a.m. and 1 p.m.? What was the first time when the water was 1 meter?
Great. So let's see if we can sketch the picture. I'm sorry I didn't provide you a graph. My graph's really nice too. I have 24 hours marked out and everything. So sorry about that. Actually, you might feel a little more freedom by having just free space to work. I don't know. You might not want to have a grid or anything. No, we're just going to draw the graph of this. That's all. So we have actually, in essence, we have kind of 2 points that were given to us, right? So what are those? Name a point. Give the coordinates of a point that we know on this graph that we can plot right away one of the points. I feel like they kind of gave us 2 points, didn't they? Give me a point. Bryn. Yeah.
Like 211, do we have to translate it into like hours after midnight, or like hours after, so like we have to translate the 11 minutes into hours?
Yeah, I mean, this is a good question. The 211 is kind of stymieing you, right? A lot of people aren't like volunteering because they're like, well, it's 211 comma 1.9. Well, that's kind of weird because I don't know how to plot 211. So what do you want to do? I'll take, this is a modeling problem, and modeling involves maybe more than anything choices along the way here. So you decide. What do you want to do with that 211? Piper says she has an idea. Okay, so you want to do it all in hours. That's a great way to do it. My last class we did it all in minutes. Everything really went swimmingly. So you could do it either way you like. But we'll do hours just for fun, okay? That'd be fun. Okay. If so, then that makes our scaling of the graph easy. That's for sure. So 1 hour, 2 hour, 3, 4, 5, 6 hours. I'll just keep track. 7, 8, 9, 10, 11, 12, 18. So I'm just going to track this for 24 hours. If you want to do it on your own in minutes, then multiply all those by 60 and you'll have it in minutes. So hours does make the scale really nice. I think I really do like hours, but it does make this time messy. If you do it in minutes, the times are a little nicer, but whatever. What'd you say this is? 2.183? Is that approximate though? It is, because it's yeah. So T is approximately 2.183. What am I asking you to do is to store that value in your calculator, use it, right, or something like that. If you're gonna use that rounded value, I don't know, or just carry it around with you in your pocket as 2 plus 11/60ths. That'd be fine too. However you want to do it, somehow make sure it's right at all times and never approximated, never rounded. Okay, whatever you do, whether you want to store the value or always type it in as 2 and 11/60ths, one way or another. All right, and then 1.9. So that's 1 point. So if we're doing this, we got 211, which is like here, and 1.9. I guess I need a scale on the y-axis. How about that? How about we make that 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. All right. So 1.9 would be like here, 211. I don't know. We definitely need to label this stuff because who knows where that point is. So 2.183 approximately, comma 1.9. All right, and then the other point is, did someone do that one for me? 814. What's 8 plus 14/60? Well, not you can't answer all the questions. What's 2 plus? Did you give me an approximate t value on that? 8 point something. 14/60. 233. All right, I'll go with that. Comma 0.4, right? So 8.233. Comma 0.4. 0.4 would be somewhere, I don't know, there. How about? Again, that's super unclear, so I'm going to actually label it. 8.233, comma 0.4. Great. And already, even though we have no idea what the equation is, I can already kind of like get a pretty good feel for what this looks like. Already. That's the first high tide. That's the first low tide. So it's going to look like this, and it'll repeat again later here, but at least I can start the graph with pretty clear confidence. That wasn't very good, sorry. It's meant to be the maximum here, sorry. You can go with me on that. Okay. Now I'm ready to do the same thing we did in the warm-up today. Give me all 4 things if you know them. Can you start with something and name it? Because we'd like to come up with a model for this. H of t, maybe, let's call it. And then these 2 questions are interesting to me, but the most interesting thing to me is the model. Like once we have the model, you can bring any question to me you like. But I need all 4 things that we did like it, just like the warm-up today. You have one, Shane? Amplitude, how'd you get it? So he did the height, the maximum height minus the lower height, and he said that's the total height of the wave, but that's 2 times what I really wanted. So he said, I think A is going to be 0.75. Agree, people out there? Anyone? Yeah.
If we do a cosine graph, then the phase shift would be 1.9.
Yeah, let's just say we're going to do a cosine graph because that seems like the lazy, nice option. The h would be what, would you say?
2.13.
Yeah, and again, let's use the full value there once we get to the point where we actually need to enter that in our equation. You have another thing for us? We're making good progress.
A is,
1.15, and tell me how you got that.
well, you can find the amplitude and then add it to the height of the lowest point.
Okay, so you did 0.4 plus 0.75 to get the k value. All right, we're almost done. We need one more thing. What would you like? What else you got for me? What do we need? The period. Oh yeah. So what's that, and how do we get it?
So,
Danny, I'm here for you. Yeah. Yeah, and we should actually maybe use the full values there too, huh? Did you use the full values? Okay. And so say it one more time. Sorry. 20 point. 20.8. We're gonna actually use the full value when we go to it. And how'd you get that? I'm trying to figure out how you got that.
So because, so you think about it like in quarters.
Okay.
The maximum and minimum would only be like 2 quarters apart. Or if you can think about it half, that's half.
That's half the period.
Yeah.
All right. So what? How'd you compute that? What is that?
So
8 point.
you add,
This.
oh, then I don't.
Yeah, I think maybe that might be a little off. But I liked your thought process. Yeah, this is half the period we're looking at right here. So whatever that is, we might double it. So, yeah, do we have calculators at the ready for this here? It's actually 12 point something. All right, I'll go with it. Again, we're going to enter these as is it exactly 12.1?
Yeah, exactly.
Exactly 12.1. All right, perfect. Here. And then that means b is what? Pi over 2 pi over 12.1, right? Or pi over 6.05 or something. I don't know. You could say it a couple. Good. We're ready to write our model down. Here we go. And we're going to just assume that it's a cosine model because someone told us to. Okay. Here we go. Again, cosine model seems to be a good way to do it. 0.75 cosine. Why? Because that's a maximum already, ready for us to go at a maximum. We'll shift to the maximum. Again, keep in mind that when we actually enter this in the calculator in a minute, we'll actually enter the full values. All right, that's the moment we're waiting for right there. Okay, grab your calculator now. Where is mine? Put it off to the side. And grab it. Let's graph this just for fun. See if we get a picture just like ours. Let's see. So 0.75 cosine of, now I'm trusting you, Cassie, that really is exact? Okay. Okay, good. X minus, now that is actually 2 plus 11 3/60ths, right? So I'm going to put it in that way. If you use the stored value, that's fine too. Plus 1.15. I think I have no rounding at all there. Window. Let's make the window like what I have. 0 to 24 hours maybe, if that's what X is. And I don't know, 0 to 2 for Y, for the depth. Something went wrong. Oh, I need another set of parentheses. There we go. Does that look good? It's looking like my graph up here, I think. We'll actually test it for sure in a second. We'll see that if we plug in 211, let's see if we really are at, let's actually hit trace. and type in 211. Are we at 1.9? Ah, good. Whew. And if we type in, what were we at? 814. If we type in 814, are we at 0.4? Good. All right, so I think we did it correctly. I think we got our model. Huh? Can I enter an equation? Oh, yeah, sure. I just entered this, except the only thing I changed was I changed that 2.183 to be like what it is. Or if you stored the value, you can use your letter, minus A or whatever letter you stored it in.
Why are you subtracting the 2.189? I thought it was like x minus 1.9.
Where'd you get 1.9?
Sorry, I'm like.
Oh, yeah, I think you're using the y coordinate, but you need to shift using the x coordinate. Yeah, yeah. All right, good. So now that we have this, we can very easily ask the questions and answer the questions that we're supposed to answer. So what was the depth at 6 a.m.? What do I trace to here? 6. Done. Write that down. 0.850, 3 sig figs, meters. And 1 p.m. So I put in 1. Oh, 13. Okay, yeah. 1.74 meters, 3 sig figs, right? So 0.850 and 1.74. I think I got those right. Meters for those two answers. And then what about B? How do we answer that question? Help me out. What's the actual process we do, not just the answer? How do we, I think you've done this like 1,000 times in your life, so remind me, how do I find the answer for one, especially if I have a calculator in front of me? How can I do this? Yeah. So maybe we just look at the graph. There's what 1 meter looks like for every time. And you can see from the graph that there are a couple of nice points where the depth of the water corresponds with that same height, 1 meter. So I think we're asking, what is it? For the first time, there are many times, but it's asking for the first time. So go ahead and do that if you haven't already. Intersect, first curve, second curve. Where does it look like it happens? Like 1, 2, 3, 4, 5 something maybe? 5.596. So that's like, what is that? 5 hours and I don't know. Let's go back to the home screen here. If you type in X, as long as you just found the intersection, X currently has that value. So type in X and press enter on your home screen. Subtract 5. So it's 5 hours and then this, and like that amount of partial hours. Multiply by 60. I feel like I've done this before in my life. So it looks like it's 5 hours and 36 approximately. 5:36 a.m. approximately. It's still an approximation. I don't know, but so 5:35 and change. Okay. Do you have anything else to say about that problem? Well, again, the powerful thing is having the model, right? Like, once you have that model, we can ask you all sorts of questions. When's the third time the water is 1.5 meters deep or something? We can ask anything once you have the model. Yeah. Go ahead. So, how do you find the what? The period. Someone review that with us again. How do we get the period? We just wrote it down over there, but no one, we didn't, Mr. Chase did not show it. How did we get it, Chase?
So you subtract the minimum from the maximum, so that's half the period.
So this 8.23 whatever minus 2.183 should be like the x distance or the t distance, the time between those two. That would be half the period though, isn't it? The whole period should be like max to another max. So I think that's 6. Yeah, so that was 6.05 if you subtract those. And if you double it, you get 12.1. So that's the period. Is that okay? All right. Can you? Does anyone have a good Scottish accent? Anybody? Kevin? Go ahead and read example number 2 for us. Go ahead. But it has to be in a Scottish accent. Or then a normal American accent would be fine. Go ahead.
The average monthly temperature amongst the Scotland is going to be
Well read. All right, so it actually, it kind of just says, here's a table, but just ignore everything. Except for what? 31 and 66. So use those 2 points, and yeah, I think it's Fahrenheit. Celsius, yeah. Scotland, it's cold. All right. So use those 2 points, and then just create the model like we did before a second ago. I'll give you a second to do it ahead of me. Go ahead. Figure out what the 4 things we need to know are. Just using those 2 points. And if you're, so we'll come up with our model just by hand with those 2 points. Does anyone out there know how to use the Sine soil regression? It's an option on the menu for you. Yeah, I mean, so I'd be interested. We'll all do it by hand with these 2 points, but if someone, 1 or 2 of you want to run the sine soil regression on all the points and see how we compare, that'd be interesting to know. Yeah, just, I don't know. If you run it on these 2 points, it should agree perfectly with our model. Amplitude. 66 minus 31. What's the period? I'm having trouble with that. Oh, is it just 12? Like, as in 12 months? Oh, that makes sense. So B is like pi over 6, I guess. 2 pi over 12. And H, what do you use for H? You have a choice. What would you like to use for H? 3? Okay. So I think we're ready to write down our model. This is fun. Capital T of little t, how about? For temperature at time t. You like that? No, it's awesome. If we have capital letters and lowercase letters, we should use them to their full advantage. All right, here we go. All right, here we go. So what is it? Amplitude is 17.5. Did you get these? Cosine of something. Pi over 6 times t minus 3 plus 48.5. Is that right? It's not quite right. Help me out, Shine. All right, so we actually meant negative 17.5 for A. All right. Could you write it as a positive one, just for fun?
Yeah.
Go ahead and do it. What do we, just for fun, let's write another model. What would it have to be?
Okay, wait, so I'm asking a question about A. So does A stand for like this amplitude, or is it like
Yeah.
always positive?
Well, I was just going to say, I mean, I kind of abused the notation here. Let's actually be careful here.
Because like I felt like the amplitude was the absolute value of A.
Yeah. But the A value could be positive or negative. Right, so the amplitude is definitely 17.5. We choose in this first example to make it negative 17.8. Right. What belongs in there? If you want to write it that way. T. What do you want to do? Huh? Minus 9. That'll work, I think. Yes. Check it. You want to write another one? Yeah, you do. No, I know, but we're having fun. We want to have as much fun as we possibly can. 9 months in the future is the same as 3 months ago, right? That's another model, right? You want to do a sine model, Grant? Come on, man. Where would you shift if you were doing a sine model? I'm actually curious because Piper's doing a sinusoidal regression back there. Yeah. What was your regression from the calculator?
Plus minus 6.
What was it?
Okay, so 16.657
I don't know. It's good enough.
Okay.
Sine.
Sine.
It does a sine model. That's what I was
yeah,
interested.
sine model. Sine 0.524.
Wait, I have a question. Is pi over 6.524? Anybody? I'm gonna guess that it is. Okay, keep going.
X plus 3.107.
Can you divide 3 point whatever that is by 0.524 for me?
6.
Is it 6 something? It's 6 something. Good. The reason I say is because I want to put parentheses there. And 6 makes sense to me too, doesn't it? Why does 6 to the left make sense if you're shifting there, or 6 to the right? Either way, right? That would be the equilibrium point. It would be in between there. Then plus something. What was the end?
Plus 50.585.
60. 50. Point something. All right, well, whatever. It's close. On the calculator, they did it a more precise one. Actually, if you look at these, and I encourage you anytime you actually do curve fitting out in the real world, to actually look at your results. Don't just like feed it to a calculator and be like, well, I don't know, it's probably right. Like actually look at them. You might actually like our by hand model better. Actually, just visually speaking. Well, it's kind of using all the points to fit it as best as possible. So I guess that it thinks the amplitude is an outlier a little bit. I don't know. Yeah, but
Why was the amplitude of the sine function different from the amplitude of the?
it's using all the points, right? So it's trying to best fit it to all the points. It doesn't guarantee that it goes through though every point, right?
Could you do a sine regression with just the 2 points that they?
And then it should agree exactly with ours, right? If you only fed it those 2 points, I think it should agree exactly. We should try it. You should try it. Let's at least say one thing about the pendulum problem at the end here. How about Laura? You want to read it for us? How high will it be? Yeah. So listen, if you want to model this, it says at 0 seconds it'll be at 23 centimeters high, right? Well, when's the next time it'll be at at 23 centimeters off the ground at its maximum height? So by a full swing, what do you want to interpret that to mean for the pendulum? I don't know.
Period.
No, I mean like actually physically. The pendulum does this, right?
Yeah.
So this is 0 seconds, and then when is it here? You want to call that 3 seconds? Or what's a full swing? I don't know. I honestly don't know. Do we want to say it's back and forth, or just forth?
Fourth.
Just forth? All right, if so, that makes our numbers easier. So we'll say that it's that 3 seconds, it's here, and then at 6 seconds, we're back here. We did the exact different, we interpreted the other way in my previous class, but whatever. I don't know what a full swing means. So then the period would be 3 seconds if we interpret it that way. All right. We've had fun. Try it. Yeah. Homework 3 tonight. All sorts of fun. Sinusoidal modeling for you.